All right, chemistry, here's your video lecture for Chapter 11, Section 1. In this section, we'll be discussing volume to mass relationships of gases. And so in this chapter, we're still going to be talking about gases. So this entire test between Chapters 10 and 11 will be all about gases. In this section, we're going to talk about volume to mass relationships. Now, that might seem vaguely familiar, but realize we have not discussed the mass of gases yet. If you think about the measurable properties of gases we've discussed so far, we've discussed the relationship between pressure and volume. That's Boyle's law. The relationship between volume and temperature. That's Charles' law. And then the relationship between pressure and temperature. That is Gay-Lussac's law. We've combined those individual gas laws into the combined gas law. We've discussed Dalton's law of partial pressures, but none of those laws have dealt with the mass of any type of gas. And so we are going to step into that realm right now. So at the end of this lecture, I want you to be able to state the law of combining volumes. I want you to state Avogadro's law and explain its significance. And remember, when I say significance, what does it signify? What does it mean? And then define standard molar volume of a gas and use it to calculate gas masses and volumes. And then use the standard molar volume to calculate the molar mass of a gas. Now, that standard molar volume is actually a statement of a quality that we've already used in previous chapters to convert, using the good old crosshairs, the factor label method, to convert between the number of moles of a gas and the volume occupied by that gas. It's 1 mole is equal to 22.41 liters of any gas. We're going to discuss where that number came from today. So let's go ahead and get started. So in 1811, the Italian scientist Amadeo Avogadro proposed the idea that equal volumes of all gases under the same conditions have the same number of particles. So I'm going to read that again. Equal volumes, and of all gases, it does not matter what gas, equal volumes have the same number of particles. Same volume means same number of particles. As long as we're talking about a gas, and as long as we're under the same conditions, same volumes have same number of particles. Now, a result of this relationship that Avogadro came up with is that molecular masses can actually be very easily determined using stoichiometric skills that we already have in this course. Later, the Italian chemist Stanislao Cannizzaro used Avogadro's principle to determine the true formulas of several gaseous compounds, including compounds that today we assume are obviously known to everyone, but they were not. They actually had to be determined, and Avogadro's law, Avogadro's research, was a huge jumping off point for that. So continuing with Avogadro's idea. Avogadro's idea turned out to be correct and is now known as Avogadro's law. So here we have another law for you to remember. Avogadro's law states that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. Again, all gases at the same conditions, right? Same temperature, same pressure. But no matter what the gas is, equal volumes have equal number of molecules. Equal volumes have equal number of molecules no matter what the gas, as long as we have the same conditions. So with this knowledge, chemists gained insight into the formulas of chemical compounds for the very first time. For example, in 1858, Cannizzaro used Avogadro's law to deduce that the correct formula for water was actually H2O. That was unknown before this time. Avogadro's law also means that gas volume is directly proportional to the number of moles of a gas at the same temperature and pressure. Okay, let's unpack that. Avogadro's law also means that gas volume directly proportional. Directly proportional. We already know what that means. It means two variables change in the same way. When one goes up, the other one goes up. When one goes down, the other one goes down. So gas volume and the number of moles change in the same way all the time, meaning if the number of moles goes up, the gas volume will go up. If the number of moles go down, the gas volume will go down, as long as we're at the same temperature and pressure. This relationship is expressed by the equation shown below, where K is a proportionality constant Now, if I were to rearrange this equation so that I were to divide both sides by n, I would have that form that seems a little bit more reminiscent of what we've seen from direct proportionalities like Charles' law and Gay-Lussac's law, where we'd have volume divided by moles is equal to K. But again, you can just algebraically rearrange these and you would come to this equation as well. Volumes of gases change with changes in temperature and pressure. It's why in all of these different statements thus far, we've said at the same conditions, at the same conditions, at the same temperature, the same pressure. Because if we change those, the volumes of the gases will change with them. According to Boyle's law, Charles's law, Gay-Lussac's law, any of those changes will affect the volume. Except for Gay-Lussac's law, that's just pressure and temperature. But all of those, both of those laws, Boyle's law and Charles' law, that affect volume, right? The things that can affect a volume are temperature and pressure. So a set of conditions has been identified for measuring the volumes of gases, right? It's a standard. A standard it's arbitrary. So they had to pick something, but it's against this thing that that scientists compare everything else. Now they chose argon. Now argon as a gas is made up of single atoms. It also had a known molar mass. That molar mass was 39.95 grams per mole. And it's a noble gas, meaning it does not readily interact with other particles around it, meaning it has very little, or at least relatively little, forces that cause it to be attracted or repelled from other gas particles, which means it's going to have a chance to behave more ideally than other types of gases. And that's what we want right here. We want more ideal behavior, get a little bit closer to that ideal behavior, because we're creating a standard. So argon was chosen. So argon, 1 mole of argon has a mass of 39.95 moles. And so when they measured out 39.95 grams of argon, it just so happens that that amount of argon inhabited 22.41 liters of space. Okay? Now this is at standard temperature and pressure, 0 degrees Celsius and 1 atmosphere of pressure. But 1 mole of argon, which is 39.95 grams of argon, took up 22.41 liters of volume. Therefore, that number, 22.41 liters, is the volume of 1 mole of any gas at STP, right? We chose argon, but it actually represents all gases because all gases are so far away that the actual mass of the individual particles is negligible. The mass of 22.41 liters of any gas at 0 degrees Celsius and a pressure of 1 atmosphere will be equal to the to the gas's molecular mass, because that 22.41 liters is defined as having 1 mole of that gas. So if we measure the mass of that sample of gas, we will now know its molecular mass.
Filled balloons with the same volume of different gases, they would all contain equal numbers of molecules. But if we weighed each balloon, we would find that they did not have the same mass. We have the same number of molecules in each balloon, but the mass of the molecules in one balloon differs from the mass of the molecules in the other balloon. This is why in air, a balloon filled with hydrogen or helium rises, and a balloon filled with carbon dioxide sinks.
So here's a chart representing what Robot Lady just talked about. So we have a balloon filled with oxygen. We have a balloon filled with carbon dioxide. We have a balloon filled with hydrogen. Right? So if we have 1 mole of each of these gases at STP, so imagine we're filling a balloon up with 1 mole of oxygen, another balloon with 1 mole of carbon dioxide, another balloon with 1 mole of hydrogen. They will all 3 of those balloons will be the exact same size. It'll be 22.4 liters. It's going to be a big balloon, don't get me wrong, but they'll all be the exact same size. Because at the same temperature and pressure, balloons of equal volume have equal number of molecules, which is 1 mole, right? 1 mole means 6.022 times 10 to the 23rd molecules of a gas in this case. But that's regardless of which gas they contain. So we have oxygen, carbon dioxide, or hydrogen. All these balloons will be the same size. All right, guys, we're going to cut this one off for section 1. I will see you next period.